Good afternoon, students. After completing the transpose of a matrix and the properties of transpose of a matrix, now today we discuss about symmetric matrices and skew-symmetric matrices. So first of all, let us consider an example of symmetric matrices. So the first condition is here, whether a matrix is symmetric or not. How can we identify? The first condition is the matrix must be a square matrix. So that's why here written you see this one. A matrix must be a square matrix, the first condition. After taking a square matrix, now any matrix, suppose if we consider, so you see here 3 by 3 matrix we consider, and here some elements are there. So how can we identify a symmetric matrix? What you have to do, just we have to transpose the result. So already we discussed transpose of a matrix, interchanging of rows and columns. So here if you see the first row is what? Root 3, 2, 3. So that's why we have to write in first column. So root 3, 2, 3. In this way we write the other two. Is it clear? After transposing a matrix, now let's check out again the matrix. If you see here, the matrix whatever we have taken at first, after transpose, the matrix remains same. Here you see root 3, 2, 3, root 3, 2, 3. The matrix are remain same or not? So that means from here what we can say, if a matrix if we transpose, after transposing, if the matrix again remains same, that means the condition is A equal to A dash, or you can say A dash equal to A. If this result we get, then we can say the matrix is a symmetric matrix. Is it clear? That means simply what we can say, if a matrix we consider and after transpose, if the results remain same, then we can say the matrix is a what? Symmetric matrix. So that's why we write here A equal to A dash. Is it clear? Okay. Now after symmetric matrix, next we discuss about the skew-symmetric matrix. For this skew-symmetric matrix, let's take an example. So here again the same condition, we need a square matrix. So we consider matrix is this one, 0 E F and minus E 0, like in this way we consider matrix. Now what you have to do, in the same way we have to transpose the result. So if you transpose the result, you see here 0 minus EF, E0 minus E, FC 0 we get. Now if we take minus from this matrix common, since we know in a matrix we can multiply scalar, so this scalar we have to multiply to each and every element. Similarly we can take common also. So that means the meaning is what? From this matrix we have to common minus 1. So if you take minus common, then the first row remains 0 EF, so that's why we write here 0 EF. And from the second row, if you take minus common, then here we get minus E, 0 and then G. And if you take 1 minus from the last one, then we get here minus F minus G 0. So that's what we write. So from each and every element we take minus common. So that means minus 1 common. So we have to write here. And now after taking common, now if you see this matrix is same as our given first, whatever we consider the first matrix, same as the first matrix. You see here the matrix whatever we have taken at starting A, after taking minus common, the matrix is remain same. So from here what we can say, in place of this one again we put A. So after transposing, if we get the matrix minus A transpose equal to minus A. That means A transpose equal to minus A you can write, or you can write A equal to minus of A transpose. If any one condition from these two, if we get, both are same, if we get this condition, then we can say the matrix is what? A skew-symmetric matrix. Is it clear? A transpose equal to minus A. So the symmetric, in case of symmetric what we get? A transpose equal to A we get, and in case of skew-symmetric what we get? A transpose equal to minus of A. Now all of you understood this one, how can we take minus common, and if condition this one satisfied here, then it is known as skew-symmetric matrix. Is it clear? Okay. Now let's take an example or as a question. This question is very important examination point of view. This question is many times asked in final exam. So you see here the question is like that: prove that all the diagonal elements of a skew-symmetric matrix are 0. That means all of you know the diagonal elements. So diagonal elements are always we consider from first row, first column, all of you know. So now for this proof, what we have to do here, first of all we have to consider a square matrix, because here it is mentioned skew-symmetric. So that means skew-symmetric or symmetric, always we have to consider a square matrix. So now here as a whole, this one already we discussed in earlier class, Aij. I is the number of rows and j is the number of columns. So as a whole, here we represent only one, but it represents a matrix. So we consider matrix A, where Aij, that means this matrix is what? A square matrix. Is it clear? Now if this matrix satisfy the condition of skew-symmetric matrix, if this matrix satisfy the skew-symmetric matrix condition, then obviously we get here A transpose equal to minus of A, because already we know this one. If you see the question, all the diagonal elements of a skew-symmetric matrix, that means a matrix must be a skew-symmetric matrix. So that's why here the condition we have to write A transpose equal to minus of A. Inside this one is written here also. If we write Aij, then it represents an element, and if you put this big bracket, then it represents a whole matrix. Okay, now after writing the condition, so you see here when we consider a matrix, if you consider only one element Aij, so minus A, in place of A we can write Ij. A transpose, A this means what? Transpose means what? The interchange of row and column. So here the number of rows is what we consider I, and the number of column is j. So A transpose means in place of I we have to write j, and in place of j we have to write I, because transpose the rows and columns, is not it? Interchange the rows and columns, so that's why ji we have to write A transpose. So A is equal to Aji equal to, we have to write minus A means Aij. Okay, now after that what you have to do, we put I equal to j. Either you can put j equal to I or I equal to j, meaning is same. If you put here, then you get I. Here in place of j we put I, in place of j we put I. So if you add these two times of ai equal to 0 and ai equal to 0. So now here the question is arise where we put I equals to j, because we need the diagonal elements. So diagonal elements are which are? The diagonal elements are either A11, 2, 3, 3. If you see this example 1, 1, 2, 2, 3, 3, these are the diagonal elements or not? So that means I and j must be equal. So that's why for that reason we have to put I equal to j. Is it clear? And from here ai equal to 0. So as a whole, if ai equal to 0, I means from 1 to n. If I equal to 1, then another one is 1. So here what we get? A110, A220, A330. In this way all the diagonal elements are 0. Is it clear? Hence this one is the proof. Okay. Now after that, now you see this theorem, and theorem is written here for any square matrix A with real number entries, A plus A transpose is a symmetric matrix, and A minus A transpose is a skew-symmetric matrix. Since we know the symmetric matrix condition is what? A transpose equal to A, and skew-symmetric condition is A transpose equal to minus of A. So these two conditions we have to satisfy here. This one is the theorem here. So now we need to prove here A plus A transpose is a symmetric matrix. So for that reason what we have to do, we have to consider this A plus A transpose as B. And now we need the transpose result here. If you consider this whole result as B, so that means we have to transpose this result now. Now B transpose. If you transpose this result, so A plus A transpose whole transpose we have to write. Since we know A plus B whole transpose equal to A transpose plus B transpose, so that's why we have to separate this one. A transpose plus, already transpose is here, so A transpose transpose. Since we know A transpose equal to what? A. So that's why in place of A transpose we write A, and it is commutative also, so that's why we can write A plus A transpose. So A plus A transpose means what? B. So when we do here transpose B transpose, then the result again we get B transpose equal to B. So from here what we can say? the given matrix, this one is the condition of symmetric, so that's why it is a symmetric matrix. So that means A plus A transpose, if we write anywhere A plus A transpose, then from there always we get a symmetric matrix. Similarly, now next one we need to prove A minus A transpose. The same condition, if you consider here C, suppose C equal to A minus A transpose. If you consider this one, now if you do transpose as a whole transpose, then the same procedure whatever we have done. So A transpose, transpose, now here A transpose minus A. So from here if you take minus common, then we write A minus A transpose. So A minus A transpose means what? C. So in this case we get C transpose equal to minus C. So which gives us a condition of skew-symmetric matrix condition. So that means from here we can easily prove these two. So A plus A transpose is the symmetric matrix and A minus A transpose is a skew-symmetric matrix. Is it clear? Okay. Now the next theorem is any square matrix can be expressed as the sum of a symmetric and a skew-symmetric matrix. Since already we proved A plus A transpose is what? Symmetric, and A minus A transpose is what? Skew-symmetric. So now here matrix A, so we have to balance this result. So how can we balance this result? So if you multiplying both symmetric and skew-symmetric by half, then half of A plus A transpose, here half of A minus A transpose. So A transpose, half of A transpose minus half of A transpose, these two cancel. So half into A, half into A. So ultimately what we get? A. So that's why for that reason we have to multiply these two by half. So half of A plus A transpose is the condition of symmetric, and skew-symmetric condition is what? Half of A minus A transpose, and which one we represent by A. So why we have written here this condition? Because if in exam, if a question given to you, any matrix given to you, and if the question is asked like in this way, express as the sum of symmetric and skew-symmetric matrices or matrix, then you have to express the result in this way. In this way you have to result. So that's why a matrix we can write half of A plus A transpose, that means half of symmetric matrix plus half of skew-symmetric matrix. In this way we can write. Is it clear? Okay. With respect to this sum of a symmetric and skew-symmetric matrix, let's take an example. Here the question is like in this way: express the matrix B. Here you see matrix B as the sum of symmetric and skew-symmetric matrices we have to express. Now for that reason what you have to do, first of all the matrix whatever given we have to write, and at the same time we have to find out the transpose. So if this matrix is here B, then the transpose is this one. Transpose means what? Interchanging of row and column. So here the first row is 2 minus 2 4, so we write this one in first column, 2 minus 2 minus 4. Similarly here the second row is minus 1 3 4, so we have to write this one in second column, minus 1 3 4. Similarly 1 minus 2 3, so here we write 1 minus 2 3. Is it clear? Now we have to express this result, this B matrix, as a symmetric and skew-symmetric. So already we know the symmetric condition is what? Half of B plus B transpose, because in theorem we write half of A plus A transpose. Similarly here the matrix is given B, so that's why we have to write half of B plus B transpose is the condition of symmetric, and the condition of skew-symmetric is what? Half of B minus B transpose. So now here what you have to do, this result we have to prove as a symmetric. That means the meaning is what? We have to consider this whole result as a P, and we have to express this one symmetric. So symmetric means what? P transpose equal to P we have to prove here. That means how can we do this one? So first of all what you have to do, first of all this half of B plus B transpose result you have to find out. So that means you have to add these two and then multiply it by half, then you get one matrix, and after getting this matrix you have to transpose it. P dash means what? Transpose it, and then let's check out what you get. If P transpose and the P value is same, then it is a symmetric matrix. Is it clear? Similarly what you have to do, the skew-symmetric condition is this one. So first of all half of B minus B transpose, so that means B minus B transpose you have to find out, and then we have to multiply it by half, then you get a matrix here, and this matrix we have to consider Q. After taking this one is Q, now what you have to do, you have to transpose this Q matrix, and after transposing if you get the result Q transpose equal to minus of Q, then it is what? A skew-symmetric matrix. Is it clear? Okay, now after getting this one, what we need to prove? We need to prove as a sum of symmetric and skew-symmetric matrix. So that's why this symmetric condition is P here we write, and skew-symmetric is Q. So what you have to do, this P and Q you have to add. P plus Q. Remember P and Q. So P, whatever the result you get, Q, whatever the result you get, you have to add these two. And after adding these two, if you see, then when you get a matrix, this matrix is again the main result. Whatever the question given to you, the same matrix you get. If you get the same matrix, whatever given at first, then your answer is correct. Otherwise, your answer is wrong. Is it clear? So in this way, we can express a matrix, the sum of a symmetric and skew-symmetric matrix. Is it clear? So now here, your task is what? The exercise, I think exercise 3.3. Yes, exercise 3.3 from question number 6 to up to question number 12. Very easy questions are there. So you have to complete. Is it clear? From exercise 6.3, from question number 6 to question number 12, you have to complete. And some example questions are also there. You have to do this one. Very easy chapter, very easy questions are there. Easily you can solve. Is it clear? So if you complete this one, in our next class we discuss about the elementary operation of a matrix. So elementary operation is another very important topic. So first of all, you have to complete this exercise 3.3. I think all of you complete the exercise 3.1 and 3.2. So next you have to complete this exercise 3.3. Is it clear? Okay, thank you.